Well, Hubert Ziegenhain gave me the okay to start, so it's a pleasure to be here in Heinitze again for the newly arrived people. This is a conference that we are organizing since 6 years, 2002, the first time when Lenka Žižková and Pavel Žižek discovered this place. I think it was used from the Prague Mathematical Statistics Group for robust conferences, and then we made it to first an explore meeting place plus institute meeting place, and now this year we take it as a forum to present theory that mostly Volodya Spokojny from the Weierstrass Institute of Applied Analysis and Stochastics has developed. He's also a member of CASE, the Center of Applied Statistics and Economics, and it is my pleasure to support him here. So everything that you see here in theoretical results, they are not really developed by myself, but he always says that I am running in front of a locomotive. He thinks he's the locomotive, and I say the contrary. I say I am the locomotive and he's running ahead of me, because I always put new problems to him that he solves. So it's a pleasure to cooperate with him here. And the idea is that we share with you a new view to statistics, which we call modern non-parametric statistics. And you know that I like these three-letter airport codes. So this code of this talk is called MNS, right? Modern non-parametric statistics. Now, a few more words about the organization. Turns out that a year ago I discovered on the internet that Berkeley and Stanford are taping classes. So I wrote to our CMS, Computer Media Service director, why are we not taping classes? I have an iPod here and I don't see any taped class from the Humboldt-University. So he said, I will take care of it, but of course it's a Prussian university, it takes some time until the locomotive runs. And finally, in last December, I have the okay that we are participating in a so-called pilot project to develop multimedia courses, and that's why we are taping everything. So I am taped, your questions are taped, the camera will swing around to your face, it will be zoomed on your thing, and if you are inactive, like Professor Spokojny, for example, he's inactive, he doesn't listen to me, and looking at this laptop, right, this is all recorded for eternity. So you better keep your laptop closed. All right, so this time, a concept that I have described in the Sonderforschungsbereich, the Collaborative Research Center 649 on economic risk, a concept of cooperation between Wrocław, Prague, and Berlin, because this is also a place which is a Polish, Czech, German meeting place. For some reason it is called Center for Spiritual Relaxation. We just call it the cloister in Heinitze. But this dream became true because I can welcome today Barbara Boros from Wrocław, and I can welcome a group around Stenek. And in addition, I'm happy to have two Taiwanese guests from the National University of Technology in Taipei. And actually, yesterday I promised Brenda, because she had a little accident, I promised her a chocolate. And because she's coming from Mexico, I thought I'd bring her some chili chocolate. This is for you, Brenda. And to welcome Barbara, because she will come to Wrocław, I have another chocolate for you. And to welcome the Taiwanese guests, I have a book for you. Come, I will sign it later. Thank you so much. Thanks. Okay. Okay, and to welcome all of you, I have a handout. So somebody has to help me here to distribute this handout. Not Brenda, because she is disabled. Somebody has to help me to take this handout. There should be enough for everybody. Okay, the handout is distributed. This handout is really is sort of my contribution to this talk, because originally the technique, or maybe 88% of the techniques that we show today, they were given in a class at CASE 2005-2006, shortly before soccer, during the winter time, and but the blackboard was very small and there was no way to record all this, and so the idea was to develop a regular class for master's or PhD students. So the first time we gave this class was in Wrocław during the Socrates program, and we will give it here the second time, and it will improve every time, I hope so. The next time we give it this year in April at the RWI, Rheinisch-Westfälisches Institut für Wirtschaftsforschung, for a PhD graduate school there, and we'll give it later this year either in Beijing and maybe in addition in Amsterdam, and also in next year in other Asian universities, like for example the National University in Singapore. So you are welcome to help us with improvements. We try to make the notation unified, but from time to time certainly we have probably not done our job perfectly, so please tell us when there's anything wrong. Now, I think I have said everything, except of course that I should say, to make such a handout in such a short time, everything is done in Wrocław, everything was done sort of live. When I was teaching, Volodya was still typing the next transparencies, and it was almost similar to that. Yesterday, noontime, the last transparencies were printed, and I would like to thank Yin Chen and Richard Song, and also Mrs. Elagin, because he will show applications that made this course possible. So let's thank them for creating this transparencies. Okay? I think now we can probably start with the course itself. I will give introduction into the basics of statistical likelihood-based or contrast-based modeling, and we'll show you a little bit of philosophy of statistical modeling. Then we go on with the modern non-parametric statistics, and you will always have, in fact, three types of theorems. When you do statistical modeling, maybe I can go to the next transparency. When you do statistical modeling, you always want to understand data. That's why you develop a model. So, what do you do? I make a very rough graph. Suppose this is your data, and you try to understand it with a very simple model, like this one here. Very simplistic. We call this a parametric model. Let's call it P theta. So we try to model the unknown probability measure. There's a probability measure involved here, the distribution, joint distribution. We try to model this with a very simple parametric family. We can try to extend this family, and what we will do is we will try to extend it with a family around it. And this distance here is measured by a condition which we call SMB, small modeling bias condition. And so these picture you have to keep in mind, because we will see today and tomorrow always three types of theorems. We will calculate theorems based on using a parametric model. That means the risk of modeling data with this parametric model under this, we call it in good Latin tradition, Procrustean bed. I hope you know this word. Procrustes was this Italian robber who was taking the people as prisoners. If they were too long, cut the legs. If they were too short, he stretched them. That's why, and he did this in a bed. We would call it, the German word would be, or the English word would be stretching bed or cutting bed, right? The Latin word is Procrustean bed, right? So certainly the parametric model, or many parametric models, will not capture the full detail, and so that's why just calculating the risk as if the model were really generated by this parametric model is not the right way to go. We always want to calculate also the risk, or would like to know what are we doing wrong under an extended model, but it shouldn't be too far away. That's why we call it small modeling bias condition. So first theorem will be about calculating the risk under a parametric model. Second type of theorem is calculating the risk under this small bias condition. That means we extend it a little bit. You can call it non-parametric if you want. And the third type of theorem is to adapt, in a sense, this borderline here to the data. That means to formulate the precision of non-parametric modeling under the small bias condition with chosen model dimension that with model selected directly from data. This is the adaptive part. So you will always see three types of models. Again, parametric, non-parametric, which is called then, there are things involved that we don't know. That's why in modern statistical literature it's called oracle type models. And then the adaptive procedure where we try, or the adaptive modeling where we try to infer from data the dimension of the model. But you will certainly see how we go along here with these three types of theory. So now let me introduce a few notations. I did it already here on the blackboard. We are talking about distribution. P, now if you look at your handout, you see that the P written with these two long stripes here, it always means that we are talking about an n-dimensional. It could be a time series, it could be an n-dimensional vector, but it's always the distribution of the whole data. And if there's just one line here, then it's just the P of one single observation. Okay, so parametric modeling, this Procrustean bed, means that P, the whole distribution here, is exactly given by a parametric model. That's parametric modeling. Non-parametric modeling means that the parameter space, or the flexibility, often I can formulate flexibility in terms of the dimension of the parameter vector, is given by possibly infinite dimensions. So P is P, it could be an infinite dimensional model.
How would you in this language describe semi-parametric?
Excuse me?
How would you in this language describe semi-parametric models?
In this language?
Yeah, in language of dimension of P.
Okay. In this case, a semi-parametric model, you would split up the vector in some known dimensions. So you would say Rp plus Rq. Yeah? So, and in a parametric model, so suppose it's Rp plus Rq, and then non-parametric part you leave one of them parametric, and the other one you make it infinite. But we are not covering this case, so we are not that far. But thanks for this comment. There are many things that we have not done yet in this, or that Volodya has not done yet. We'll see. Now you can decide whether you are the locomotive or whether you are the guy who is running in front of the locomotive, right? You can discuss this later with Volodya. Okay, so I told you understanding data via statistics is modeling. It involves model choice. Yeah? And I told you this model choice. Many of you know Akaiki's criterion, for example, or parametric model choice procedures. What they are doing is they take a fixed model that is sequentially extended. Here, in this case, we are choosing sort of this boundary from the data. As I say, standard procedure is to apply many low-dimensional models, example AIC, and select one which fits best, for example, by AIC criteria. And the procedure that we will show you today, they use very flexible model classes. It is formulated in a very general language. It depends on so-called weights, which you can think of when you are trained as a classical smoother. You can think of kernel weights, but they can be much more flexible. Must not be generated by kernels, could be generated by k-nearest neighbor weights, for example. The aim is to control the estimation risk, and then this will be mostly demonstrated by examples. We will show that the procedures are somehow computationally involved because the selection procedure to select this boundary, to say so, to make the adaptive step, we need to calculate a sequence of critical values that we are generating by computer. So the value of this today's theorem, another important theoretical step forward in this theory is that Volodya was able for the first time, I think in the literature, to give risk bounds with simulated critical values. Okay, so let me now start with the basics, the classical parametric approach, or you can call it likelihood in a nutshell. Then we'll talk about regression, oracle, and adaptive procedures will be later tonight or tomorrow, and we will give several practical examples. This part of the course will probably be done by Mrs. Lavenagin, and we'll give several applications, especially to volatility estimation. Another example for who is ahead of the locomotive or behind the locomotive is the ADACOP project, the Adaptive Cupola project, which has been tentatively accepted by the Journal of Business and Economic Statistics, a very good A journal. This is joint work of Enzo, Giacomini, Volodya, and myself. But the referee, we had a good referee, he immediately saw it's a good procedure, but there's no theory yet. So again, you may decide who is ahead of the locomotive or who is behind the locomotive. Okay, now, very simple parametric modeling to make you warm about notation and to warm you up with notation and to get you involved into the way we are developing theory here. Suppose you get some data here, you get training data points. So I repeat the notation. Yn is the vector of y1 up to yn. What means parametric modeling? For a single observation, recall there's no double line here, so one line. So a single observation is parameterized by a probability measure with one parameter p. So for example, it could be this simple phi of y minus theta. I hope everybody understands that. That's Berlin notation. I don't know whether they use var-phi or phi in Prague, but this is the PDF of a normal, standard normal distribution. So this could be one parametric modeling. This is called then a Gaussian shift model. Or for n observations, the likelihood would be just the product of these densities if you assume that these 20 observations are independently, identically distributed with this Gaussian shift model. So here's a very simple example. So here you are 20 observations. I guess this is done with Explore. Maybe it looks like Stenek's graphics that he developed. This is box plot. Here you have your observations, and you are trying to fit a distribution to these observations. Here for 20, here for 200. So you see the distribution here. If you you can parameterize this in this. If you assume your parametric model is just given by a standard normal density that you just shift around, then all you need to do is to estimate somehow this center of the distribution. Okay, so I will do it for you once to, again, warm you up for the notation. We are talking here about the standard normal density. We are talking about the so-called Gaussian shift model. There should be Gaussian here. Right? The Gaussian shift model. So the p theta is given by phi y minus theta. P is one-dimensional. P could be also two-dimensional in a shift scale model. Then I would have the standard deviation here, and the parameter vector would be mu and sigma, and dimension would be 2. Here you have an example. Here p equal to 1. That means this is just the Gaussian distribution, standard normal just shifted. And here in the second part, you have a two-dimensional parameter vector where you also scale. These are classical examples. I think you have no problems with that. This course, I told you that the three-letter code is MNS. The quantlets, or somebody said matlablets, or is there a word for R? R macros? Anyway, the quantlets, that's a nice name. The quantlets will be available. We have them actually here, but this computer is from the local conference center, so it does neither have R nor MATLAB nor Explore, so I cannot show it to you. But you will see many examples, not such simple ones, of course, tomorrow. That will be presented by Mr. Slack. Yeah? Okay. Now, this was parametric modeling, finite dimensional modeling. So I explained to you now in a very simple setup how infinite dimensional modeling comes into play. Okay? So suppose you have n observations again, and they have a certain distribution with PDF f, but now suppose this density is not given by such a simple parametric Gaussian family, but it lies in a more complex space like this one here. So then you have density f, and of course it integrates to 1, and it is nicely, it is not too rough, so that maybe the L2 norm, one possibility, the L2 norm exists. So you could make, you could write this as a Fourier expansion, and so you see this density, this unknown density, is actually can be thought of as an infinite dimensional Fourier series, and now with size, the orthonormal basis of this function space that you're looking at. Now you see the parameter vector is infinite. So we are in this case, so we have a possibly infinite parameter space. Now let's see how this non-parametric modeling looks like. For example, such a mixture model. You have two unknown distributions that you mix together. In this case, actually, I know it because it is simulated. And non-parametric modeling means that you are trying to select the dimension here of Fourier series. Okay, capital J, there should be probably a J hat here. And you try to estimate the Fourier coefficients. And the question is now, what is a good theta, what is a good psi, and what is a good J? And this kind of question will be answered by the theorems given today and tomorrow. So but the basic idea is that going from parametric to non-parametric means that you make the dimension of the modeling approach flexible. And the adaptive part is the part that tells you how flexible you should do it. Yeah? If you know everything, so for example, in this case, if you would know the true distribution, yeah? Suppose you know this curve here, this black curve here, because you simulated it, right? Then, for a given sample size n, there is, in a certain sense, which we will not define for this example, but in a certain sense, you believe me, certainly, there is a good, or we will call it optimal, J and a good theta that will, in a L2 sense maybe, or in some distance or divergence measure that we have to define, will approximate the black curve very well. Okay? It will be a function of n. Yeah? And this will be, in our later language, this will be called the oracle estimate. And the oracle one, where we have to know sort of the true distribution, this one is called in your handout, is denoted with a star. So we can look whenever there's a star. It's something that we cannot calculate from the data, because it depends on the true unknown distribution. But we could say God can calculate it because he knows the true unknown distribution. What we are doing is we show later how to approximate these oracle distribution and calculate the corresponding risk. Now a few more notations. Parametric model has this. Now I'm sorry. Now I said something about theta star, the oracle estimate. This is a true parametric model here. So we have here also we use theta star here for the true parametric model. So suppose the distribution comes from this box. Yeah, that's what is here. Okay. Suppose it's absolutely continuous for some measure p. So you can calculate the log likelihood. Yeah. Sorry, I have to kill this. Calculate the log likelihood. The log likelihood, when you look at your handout, for some reason that I don't understand, it is the log likelihood is called capital L. Usually in the British literature, it's a small l, but here in this course it's a capital L. Okay. So log likelihood is L. We will also be talking about the likelihood ratio, but when we calculate with respect to some fixed theta 0, that's the likelihood ratio. Logarithm of ratio is the difference between the logarithms. That's what you see here. This is called L theta 0. Okay? So you can equivalently write the very classical maximum likelihood estimate. You can equivalently write it as the maximum of this function or the maximum of this log likelihood ratio. Yeah? And look at your handout. Please check that the maximum likelihood estimate is denoted in your handout as theta wiggle. I hope it is somewhere written. Do you see it somewhere? Unfortunately, it says local estimate, so it's on 0.5. We have not optimized the notation handout here. Okay? Maximum likelihood estimate. Maximum likelihood is one principle to estimate parameters. Another one is a so-called minimum contrast estimate, where one takes a contrast function, C, depending on the data and the parameter vector, and again, theta Wickel is defined as a minimum of this contrast function. If the contrast function is just minus the likelihood, then this minimum contrast estimate is of course equivalent to the maximum likelihood estimate. Give you an example for a simple contrast function so that you see how these are connected. Take for example a double exponential with PDF 1/2 e to the minus y minus x. So it looks like, some people call this a Laplace distribution. It is very peaky in the middle, around theta in this case, and it levels out exponentially. Here's the likelihood function, and the log likelihood function is easy to calculate. You just hit it with the logarithm, the product becomes a sum, and you see this guy does not depend on the theta, so you could say I either minimize this one, and you can call it a minimum contrast function, or this one, which doesn't really matter because it doesn't depend on theta, then it is just the maximum, the likelihood function. How does a likelihood look like? Here, for example, for n11, this would be a Gaussian likelihood function, L of theta. So the maximum would be my maximum likelihood estimate. Okay? Different contrast functions are given by so-called LAD, least absolute deviations. Here in the case of regression, suppose you take a least squares estimate, then you are minimizing the difference between the data in a regression context minus f. This is a parametric regression function, the linear function, for example, and you square it, or you take absolute values, then you call it the least absolute deviation estimate, or LAD estimate. In both cases, you look for the minimum with respect to theta. Is anybody an idea from the transparency that I showed you before, when this would be the maximum likelihood estimate, or this would be the maximum likelihood estimate? It's very simple. Just check your tiredness level. Huh? Why does one look? I mean, people from production answer because they are very much in robust thinking. Right? Why does one look at this one instead of that one in certain situations? Exactly, the outliers. Yes, yes. And when do you expect many outliers? When the distribution of the errors is fat-tailed. So, is the normal distribution fat-tailed? Okay, so then we do this one, and a little bit fatter tailed than the normal distribution is the... Huh? You just had it here. No, yep, little bit fatter tailed is this one, right? It doesn't go off with a square, it just goes on with e to the minus y. So, in fact, if you would have double exponential errors, then in a regression model, this would be the likelihood function. In any case, the answer was right. We'll see more examples of this kind soon. But now, in parametric families, a little bit more notation and a little bit more development of the main themes, why we are interested in calculating the risk, or you could call it the distance, the precision of the model that you are estimating, and the true distribution. And why are we interested in that? We are interested often to calculate the variation of the estimated parameter, which leads you to confidence intervals. And here's a very simple example. It's the Gaussian shift example again. So take y1 to yn BIID. So they follow the so-called Gaussian shift model. So epsilon I normal, as you see here, and variance suppose is known. Then the likelihood, this is something that one learns in our faculty in the second semester. It's very simple. Likelihood function, and you can see when you take derivatives with respect to theta, you see the maximum likelihood estimate is just the mean value of the y variable. And since the mean, here, is just theta star, you see it cancels out, you have n times the mean, cancels out with that one. And the epsilon is, as you see here, n0 sigma squared. Then you see that the variation here is sigma, again cancels out with the n here, n to the minus 1/2 psi, where psi is a standard normal variable. It's a very well-known result. So what does this say? It says the maximum likelihood estimate varies, it's the variation, around the true parameter, it's the true parameter, with a speed of n to the minus 1/2. So you can see already where we are going. We are looking at how well this is sort of gives us the precision, how well we are estimating with our maximum likelihood estimate, how well we are estimating the theta star. Okay. Now, how well are we estimating? We can say this how well we are doing that in terms of the involved risk. Okay? So here you see the first time, the first leitmotiv, Leitthema. This is an English word, leitmotiv, a French word also. The leitmotiv is that we are calculating the first type of theorem, we are calculating the expected value under an exact parametric model. Calculating exact parametric model, we're calculating some distance. In this case, it's actually it should be 2r. Here is a typo, my error. I found it half an hour ago. So this constant is different in your handout. So in your handout it says CR is equal to E psi 2R. So the handout is correct, this slide is totally wrong. But we will correct it interactively together. It's semi-right and so. Semi-right in the sense that you have to divide here by 2. You have to divide here by 2 and here by 2. Then you have the concordance with your handout. But let me explain you the topic one more time. The first type of theorem, we calculate some distance and just call it here distance, and this, let me abbreviate it, distance, we can abbreviate conveniently. It's not in your handout, it's very loosely said, say theta equal theta star, so I put it like this. So this is the first type of leitmotiv. Second type of leitmotiv will be when we are outside here with the true data distribution under small bias condition. Then we will calculate this expected value, but now under this distribution outside, now it is no longer the parametric model, it is the true. Right? So I could also write here p theta star, again here distance. And I don't want to talk about the estimators here right now, but it will be the oracle estimate here. And the third type of theorem will be, again, the distance under the true distribution, but with an adaptive estimate. So this is the first time that you see the leitmotiv. Leitmotiv says, look at some kind of distance. In this case, it's the rth deviation between the maximum likelihood estimate and the true parameter. So this should read as E theta equal theta star 2r, sigma 2r, n to the minus r, cr. And your handout says correctly CR E psi 2r. Okay, so this is C1/2. This was the semi-right thing. No, it's wrong?
That's exactly what will happen.
This is wrong.
That's what will happen here.
What does that mean? In the handout? No. You forget there, you misunderstand what I mean with handout. I mean this handout, the cover page, where we have notation. That's what I mean. I'm sorry. Now I see my language problem. Look at the cover page. It's cover page, it's page number 05. It says CR equal, I mean notation handout, yeah? It says on 02, this is a handout with all the notations. That's why I refer to it. Okay, so this is correct. The first page is correct. Yeah? So in all the notation later that you will see, CR means the 2R moment of Xi. Yeah? Anyway, it's just a scaling. Don't worry. So it tells you something in a very simple model, how far the maximum likelihood estimate and the theta star are, how distant they are. Okay? Okay. Now, how do I construct a confidence interval? A confidence interval I construct by the observation that here I have this psi, here I have this psi, and if I fiddle around with this psi and look for the quantile, this 1 minus alpha quantile of this psi, I can calculate the so-called alpha confidence interval by taking the maximum likelihood estimate for the moment I assume sigma to be known. I subtract exactly this speed, n to the minus 1/2, times this z alpha. It's an exact, it will be an exact confidence interval because everything is known here, and it is for finite and it's not asymptotic. So an alpha confidence interval for the parameter given graphically in this form is plus sigma into the minus 1/2 z alpha. Okay. Now we will use this construction one more time by calculating a so-called likelihood-based confidence set. The likelihood-based confidence set is a random set E alpha. You saw just one of these random sets, but now we'll construct it differently. But but you will see it leads in this case to the same E alpha. So E alpha, a confidence set, is that random set that contains the true parameter under theta star with probability greater equivalent minus alpha. It's very simple to see that this confidence set here of 2 is really a confidence set to level alpha. Just calculate theta star in E alpha under theta star. You plug in what is the confidence set. Then you take the sigma, you take this difference down here, theta equal minus theta star, divide by sigma, multiply with square root of n. So this is something that I learned in Heidelberg 20 years ago or 25 years ago. One always has to think in terms of square root of n theta equal maximum likelihood estimate minus theta star, and this will be a normal distribution. So central limit theorem, if this were not already normal, in central limit theorem you would say this one converges to 1 minus alpha, where this is the quantile from the asymptotic normal distribution. In this case it's not asymptotic, it's exactly standard normal. Okay? Okay, now to this likelihood-based confidence, because later all the considerations that we'll be doing about this D will be in terms of likelihood. Likelihood under true model, in this case parametric, or the non-parametric model, and the corresponding closest parametric estimate. I'll show you how the connection is between the likelihood-based confidence set and the confidence set that we just calculated before. We consider the likelihood ratio, L theta wiggle minus L theta. The likelihood ratio in this Gaussian shift case has a very simple form. It is n times sigma to the minus 2 theta wiggle minus theta squared over 2. Okay? Now this formula we already proved. This is from 2. So we can see 2 times the likelihood ratio, but now we calculate the likelihood ratio with respect to the true parameter. Is exactly, see this 2 cancels out, it's the 2 here, is exactly the squared, it's exactly the squared distance between theta wiggle and theta star. Okay? That's why we are so much interested in That's why we are so much interested in having here 2r than we calculated for r equals 1. Right? Okay, so in this case we get, because this is just psi squared, we get a chi-square variable with 1 degree of freedom. Okay? Suppose now I take a chi-square variable, 1 degree of freedom, and I calculate its alpha quantile. Just tabulate it. Calculate the alpha quantile. Z alpha. This will be the notation used throughout here. And now I define myself another confidence set. For the moment it's another confidence set. You will see it will boil down to the same one as 2, but now it's a confidence set in terms of the likelihood. So it's 2 times likelihood, theta wiggle, and here all u's that are less equal than the same. Of course, in this case I can just calculate the set alpha. It is the quantile from the chi-square distribution. So now let's see whether this is a confidence set. Let's see, do we have, we don't calculate it here. No, we don't calculate it, but it's not hard to see that it is based on this formula. We take the square root, it is exactly the same confidence set as before. Now, some more details on this likelihood ratio, L theta wiggle, L theta. So, L theta wiggle, L theta, if you write down the likelihood, some terms cancel. This is just the likelihood under theta wiggle, this is the likelihood under theta. Of course, you do the usual trick, binomial formula. In this case, we plug in theta. When you plug in theta, you see terms cancel out, namely this term cancels out. So you have the distance between theta wiggle and theta, and you have the middle term, and it is not hard to see that this last term is equal to 0 by the definition of theta wiggle. Why? Because this here, sum of I equals 1 to n, this is of course independent of I, so it can be before the sum. Sum here of theta wiggle gives, I see that we need another coffee break here. It just gives n times theta wiggle, okay? And the sum of I equal 1 to yi, I also can say this is n times theta wiggle, because theta wiggle was just the mean of the y. So this is equal to 0, okay? So the likelihood, log likelihood ratio with respect to theta is given by this squared deviation. Okay, a few more remarks on different models, and then we'll make a break. I just heard a sign here that the cassette is going to be finished. So let's take a Bernoulli random variable. Bernoulli random variable is one coin tossing variable where you have probability y equal to 1 theta, y equal to 0 is 1 minus theta. The likelihood, again, is very simple to be written as theta to the power of yi, 1 minus theta to the power of 1 minus yi. If you take logs, so log likelihood, it has this very well-known form. You see, again, another leitmotif for the families of parametric models that we are looking at. You will have the sum of yi's playing a role. We call it capital S. So capital S is the sum of the yi's times log theta, 1 minus theta, and another term depending on theta. It's not hard to see how the maximum likelihood estimate can be calculated. You calculate the derivative with respect to theta. It's not hard to see. The derivative with respect to theta from logarithm is given here, and this has to be equal to 0, and you will get the maximum likelihood estimate is S divided by N. Okay? And this transparency is not the transparency we wanted to have. We didn't have the time to do it. We wanted to write down the likelihood-based confidence set. But here it is just the alpha confidence set based on the asymptotic theory. Another thing that I didn't mention is all these three types of theorems involving the distance between two parameters and true model and estimated model will all be given not in an asymptotic sense, they are all valid for finite n. Okay, so this word, center limit theorem, does not belong here. We did not have time to update this transparency in the way we wanted to have it. But you will see probably later a little story who was Kullback and who was Leibler, because here you will see already another important element of how we are defining this distance. Yeah? You saw that we were going likelihood based. This distance here, likelihood based, this distance or divergence is actually given by n times the so-called Kullback-Leibler divergence for the Bernoulli laws. And the Kullback-Leibler divergence, if you don't know it, it is given for you on page 04. Usually we call it capital K, P, Q. Okay, so in the next version of the transparencies, or maybe you can do this tonight over some beer, you can prove that this is exactly from 0.4, that this is exactly the Kullback-Leibler divergence for two parametric Bernoulli laws with parameter theta and theta prime. Okay, this is not what I don't want to show. Kullback-Leibler divergence measures the distance and the connection to likelihood is given on this transparency. So, Kullback-Leibler divergence measures a distance, it's rather divergence. Everybody in this room probably knows why I say divergence instead of distance. The problem is this. You know what that means? When you have a distance, right, between P and Q, it should be the same distance between Q and P, right? And this is not true for Kullback-Leibler divergence, right? So it's a measure of discrepancy, but it's not a symmetric measure for discrepancy. But usually, excuse me. Usually we have in the denominator always sort of the null hypothesis, right? This is the way you go. So that's why there's no problem in statistics when things always in terms of a null versus an alternative. So it is in a sense fixed. So that's why this distance, this word distance, is in quotation marks here. Yeah? It's not a distance, it's a distance in quotation marks. Maybe one should call it here already a divergence. This is your definition of 0.4. And in terms of a parametric model, we also say K theta prime, which is another possible improvement. No, it's there. It's also on 0.4. This formula is also on 0.4 in terms of a probability density function P y theta. You can see for one single observation. See, that's why you have here an E without double line for one single observation. Kullback-Leibler is exactly equal to E theta log likelihood. It's a small L for one single observation. But when you go to the whole sample with n observations, then the E becomes with double lines. Then you have this n. Okay? So again, the discovery that we made here for the first time, there is a connection between likelihood ratio, L theta equals theta, in terms of the Gaussian shift, it's exactly equal to that one, right? We have calculated it 2 or 3 times. It is n times the Kullback-Leibler divergence. Okay, let me finish this part by showing you 2 pictures that Richard found on the internet. You see Dr. Salomon Kulbach here on the left, I hope, and Richard Leibler on the right. They were mathematicians and cryptanalysts. Interesting word. Okay. You should. Do you know which university they were, Richard?
From the Theoretic Intelligence.
Princeton.
CIA.
They were at CIA. They were at Princeton. Okay, good. All right. This we owe to Zdenek. This is a nice little picture here. You use it in Prague still, I guess, for making summaries?
It's from my homepage.
It's from your homepage. Yeah. So this is Zdenek's design, but I thought it's so nice. So let me make a little summary for this part. Likelihood-based confidence interval for the Gaussian shift is given by this confidence set. So we take 2 times the likelihood ratio, calculate, there we plug in the maximum likelihood estimate, and you calculate the free parameter u relative to critical value with set alpha. Kullback-Leibler divergence for a parametric model is equal to the expected value of the likelihood ratio, and the discovery in the Gaussian shift was that for the full model it is n times the Kullback-Leibler distance between theta and theta. Okay, now we make a break, and then we pick up with more complicated models, and we'll go to exponential families. Then more or less in half an hour we'll be finished with the likelihood in a nutshell, and then Volodya will probably present one of the first theorems of type 1, 2, and 3. Okay, thank you very much.